I'm studying entry, descent, and landing systems, and I'm going to talk to you a little bit about a technique which I and my colleagues are using at the Rapid Design of Systems Laboratory at Purdue University to try to increase the total mass limit that we can land on Mars in order to enable human exploration. So by way of background, just a little bit about EDL and why we care about this problem. Since the 1960s, there have been 13 attempts to soft land a spacecraft on the surface of Mars. That's by both Russia, NASA, and the European Space Agency. And of those attempts, 5 of them have met with disaster, failing sometime in the EDL process. So statistically speaking, that makes EDL as hazardous as launch in terms of mission failure. So it is absolutely a dangerous phase that we need to address when we're landing human beings on Mars. Now there are several dangers, and where they crop up are in the 3 different phases of EDL as we commonly divide them. The initial deceleration phase, where you decelerate from orbital velocity down to hypersonic, so Mach 4 to 5 or so, using principally aerodynamic methods such as large heat shields. Followed by the transonic and subsonic phase, where you use a large parachute or other decelerator, including just your aeroshell. And finally, the terminal guidance and landing phase, where you use either retropropulsive jets, airbags, as in Curiosities and Spirit and Pathfinder, or most recently the Sky Crane system from the Mars Science Lab. The point I'd like to emphasize, though, is that since the very first probes have landed on Mars, there's been no innovation in EDL systems above this level. The progression of EDL tech has only taken place down here. We are still using the same methodology, though, to decelerate from hypersonic velocities down to transonic velocities, and even all the way down to transonic velocities, really up until MSL. MSL was the first probe that even ventured above this level by using directed lift in order to control its landing site. So there is not much work being done in the early phases of entry, descent, and landing, where there is a lot of optimization to be done. And we care about this because since the 1960s, this is the course of, this is all the progress that has been made in landing large masses on Mars. We've gone from 360 kilograms with the very first Mars probes from the Russian Space Agency up to just under a ton with Curiosity. That's 50 years of research that's gone into this problem, and that's all we've done. We've only gone up by a factor of 3. And how high do we need to go to get crewed payloads onto the surface of Mars? Double this axis, bring this axis up by 2 orders of magnitude. This is Mars 1's plan, about 8 metric tons. Mars Semi-Direct, 11 metric tons. Mars Direct, about 28 tons. And the DRA-5 at 103. But who believes DRA-5? It's just up there as a point of reference. But either way, that is 2 orders of magnitude larger than the largest thing we've ever landed on Mars. So this is, as we say in system design, a problem. This is something that needs to be solved, because it is at the moment one of the largest roadblocks on landing any crewed vehicle on the surface of Mars. And I'd also like to point out that Dr. Zubrin mentioned earlier this morning about some of the agitation to go to Phobos before going to Mars. This is part of the source of it. It's not that Phobos is a better place than Mars. It's not that Phobos is a necessary prerequisite to Mars. It's that Phobos is the next best place to Mars if you can't solve the EDL problem. Because not only is Phobos close enough to Mars to conduct a robotic exploration with low mass payloads like these, it's also the largest repository of Martian material in the solar system other than Mars. Material that's been kicked up by asteroid impacts from the equator of Mars has deposited itself on Phobos. So that's where some of the agitation for Phobos first is coming from. It's not because Phobos is a good target, it's because it's the only target we can reach at the moment, because we do not know how to get this much mass onto the surface of Mars yet. And we've known this has been a problem for a long time, and there are a lot of people who are working very hard to solve the problem, but we're not there yet. And this is one of the problems that we're trying to play a part in at RDSL at Purdue. So some of the architectures which are under consideration, you can lump them into kind of 4 general categories. You can increase your drag area with an inflatable heat shield. This is something which the group at JPL is trying to do with the low-density supersonic decelerator. If you remember, a couple of weeks ago, there was a test flight out of the missile range in Hawaii, testing one of these inflatable decelerators. People are also looking at rigid deployables, rigid structures you can open like an umbrella. There's a group at Ames working with the arrest concept, trying to do that. SpaceX is very interested in supersonic retropropulsion with the Dragon and Draco engines. And different groups are looking at using lifting bodies, including our own. So in theory, these architectures are capable of getting 40 metric tons onto the surface of Mars. So in theory, they're capable of doing what needs to be done. The problem is that while in theory they're capable of doing that, they're impossible to give an operational test to unless you send them to Mars. The situations in which they work are so complicated and so unusual that there's no way to do a full-scale end-to-end test of them short of sending it to Mars. And mission planners are naturally conservative. They are not going to make a complete architecture change in their EDL system unless they absolutely need to. The kicking and screaming that went into getting Skycrane approved, just for that small change in architecture, was enormous. And mission planners are not going to take a huge risk on a new architecture system like this on their $2 billion space probe. In addition to that, the physics of all these systems is not something you can make easily amenable to design-based rough calculations. It involves fields like hypersonic aerothermodynamics and aeroelastics, things which there are no really good approximations for. And as such, any analysis of the system you do that doesn't involve $10 million of CFD work is going to be very crude. And there's nothing wrong with crude approximations in the design phase, provided the system you're designing is robust against the errors that these approximations induce. And EDL is not an imprecise field. The systems have very small margins for error, and they also have an enormous design space in terms of available trajectories and possibilities for landing. So the combination of these three factors is really a barrier to new EDL architectures being developed that we need. So the problem we're trying to address at RSDL is, given an arbitrary EDL architecture, could be an aerodynamic decelerator, could be a lifting body, could be retropropulsion, we don't know. Given an arbitrary EDL architecture, how do we optimize it and then identify a way to operate it that is both robust and reliable, so it will be appealing to mission designers and systems engineers? So the way we're investigating, the way that we think is the most profitable way forward in solving this problem is an approach called optimal control theory. Now, you're probably familiar with control theory just as a general engineering discipline. You're probably familiar with transfer functions and Bode plots, and all that is the realm of classical control theory. The question is, if we want to fly a certain reference trajectory, we want to fly from point A to point B and take path R along that path. Modeling the control system and modeling the spacecraft and implementing a basic closed-loop control, what control inputs are necessary in order to fly that trajectory? That's classical control theory. What steering inputs are necessary to give the desired trajectory? That's not what we're doing. Instead, we're asking the question, what is the desired trajectory? Because this is still in the early design phase. This is meant to provide a means of designing an entire mission architecture and trajectory, not flying the vehicle at a known answer because we don't know the answer yet. So optimal control theory is distinct from classical control theory in this sense, and we think it is a profitable way to solve this problem. So just a quick two-slide primer on the math, and then I promise there will be no more equations after that. The way optimal control theory is analyzed is we have some scalar, which could be called a Hamiltonian. It's similar to the Hamiltonian from dynamics, but it is not identical. But if it helps to think of it as the energy function in a simple dynamics course, you can think of it that way. And then we implement some state in the system. So state can be position, it can be velocity, it can be it is whatever relevant state properties you care about. Then we implement some control parameters, so that is usually pitch, roll, thrust. It's whatever you have control over on your vehicle, and then exists at all times from entry interface to touchdown. What optimal control theory says, if you can find a control history, if you can find a U at all t that satisfies, that creates an H such that it satisfies these three conditions, so two differential conditions and one algebraic condition, if you can generate a control history which produces a Hamiltonian which has these properties, that control history is demonstrably will demonstrably produce the minimum value of H. So it is demonstrably the lowest value of H for any arbitrary control history. So then the question then becomes, well, how do you construct a useful H? How do you construct something which is useful to minimize? And I won't go into that, but the point is you can construct a function h that can be all sorts of useful things, like time of flight. How do I get from A to B in the least possible time, subject to the constraint that I can't go through this, that I can't go through here or here, and I can't go faster than this? Or how do I get from point A to point B without exceeding a certain G load and crushing the crew or destroying the structure? Or how do I get from point A to point B and minimize my velocity at touchdown? These are all things which can be incorporated into the Hamiltonian and then minimized via the techniques of optimal control theory. And if this isn't clear, don't worry about it. The textbook on this topic pulls no punches about it and says if you don't get it, it's okay. It's like quantum mechanics. If you think you understand it, you don't understand it. So that's perfectly okay. The thing to take away from this is that optimal control theory, unlike classical control theory, lets you treat trajectory problems as boundary value problems and solve them with all the techniques of differential equations and all the numerical solving techniques that go along with that. It makes the challenge of finding an optimal trajectory much, much simpler than it otherwise might be. So what does this get us? What does this get us that the classical control approach might not get us? Well, one advantage is a higher tolerance to perturbations that you might experience during entry, descent, and landing. So, for example, all previous EDL methods, and this is not just for bars. This includes terrestrial EDL as well. So we're going all the way back to Apollo. All the approaches there involve pre-calculating the trajectory you want to fly. So before you even reach entry interface, the trajectory that you want your vehicle to fly is calculated on the ground, uploaded to the vehicle, and then it's not changed. As you fly then, the computer then keeps track of your relative position into the trajectory you want to fly and applies the necessary corrections. That's classical. But what happens if you deviate? What happens if something goes wrong? If a thruster gives out, or you impact a pocket of air that is denser than you expect and more rapidly decelerate than you anticipate? For small perturbations, normal control theory would then just apply. It would either raise the pitch slightly, so you get slightly higher lift and you come back on your trajectory, or if you're doing this propulsively, increase thrust and bring yourself back onto the trajectory. But what if your perturbation is large? Well, the classical control approach would then be apply a higher pitch and fly back to your preset trajectory. But what if you can't do that? What if this turn is so intense that it involves a G load that your spacecraft can't take? Or what if you don't have enough fuel in order to accomplish this? Classical control pays no heed to these type of constraints that exist in the real world. The optimal control approach would be to reevaluate this problem and say, okay, let's treat my current state as the boundary value to our new problem. This is where I am, this is how fast I'm going, and this is where I want to be. Let's calculate a new optimal trajectory, which could be any arbitrary trajectory. It's not always clear what the optimal trajectory is, and then fly to that. Now, why don't we do this now? We don't do this now because trajectory calculations generally take a huge computer cluster in minutes to hours to compute. And EDL typically only lasts a couple of minutes. There's no way to implement this in practice with a classical control approach with the amount of computational power that's likely to be available on a spacecraft. Optimal control methods, however, again, are just classical boundary value problems. They're much more easy to evaluate in short periods of time, and they're much easier to solve in real time as the trajectory changes. So it kind of allows the spacecraft to roll with the punches that EDL might throw at you and make a more robust system. Another advantage in terms of rapid computation, an excellent example of this, comes from the Prompt Global Strike program. And this is an example which was provided by one of my colleagues at the RDSL, Thomas Antony. Now, the Prompt Global Strike program is a weapon idea by the Air Force which wants to deliver a cruise missile anywhere on the planet in 1 hour. And it turns out that the equations of motion of this problem are exactly the same as they are for entry, descent, and landing. So how do we kill anyone anywhere on the planet in an hour is exactly the same problem mathematically as how do we save humanity by getting us on another planet. I thought that was hilarious when I first saw it. The only thing you change is the boundary condition. If you're making a weapon, you want the final boundary condition to be as fast as possible. You want your weapon to hit the ground as fast as possible. If you're doing EDL, you just set your boundary condition, your terminal boundary condition to 0. You want to land with 0 velocity instead of huge velocities. And it turns out the techniques which my colleague developed for this program, for, say, launching from an arbitrary point, avoiding regions where there will be ground radar coverage or you're not allowed to fly over, impacting with the highest velocity, not exceeding the thermal constraints which are placed by your TPS material, not turning so fast that your G load exceeds the load of your spacecraft. These are exactly the same problems. And he developed a manner to compute trajectories in real time on the spacecraft or on the weapon, where the constraints are all the relevant considerations for EDL. And it turns out that it allows trajectories to be computed on board in a matter of seconds, which is exactly what we need for a robust EDL system via optimal control theory. Another application is in supersonic retropropulsion with SpaceX. Now, we're all familiar with what SpaceX wants to do. We want to land a spacecraft purely propulsively without any airbags or touchdowns in the water or parachutes. But the question is, well, what if we fire these engines higher up and we're still moving supersonically? Would that enable a spacecraft to land like a Dragon on Mars? And it turns out the answer is yes. You simply treat thrust as the relevant control parameter in the optimal control approach. And you can get a control history which is necessary for landing a Dragon on Mars. This is part of my work. Decelerating a Dragon spacecraft down to the surface of Mars using purely retropropulsive techniques. No drag at all. This does not involve atmospheric drag. This is purely retropropulsive. And again, this allows rapid computation in near real time, as opposed to a preset trajectory that you have to fly, whether it's the right trajectory to fly or not. Another example, provided by my colleague Shitish Mal, who also works in the RDSL, is the question of using a lofting maneuver to decelerate a large vehicle to the surface of Mars. So in this case, we have 3 different phases of different constraints. Instead of applying one constraint the entire time, you apply 3 different constraints at 3 different phases. So first you control in all times, however, your control is your pitch angle. That's the relevant control parameter here. In this case, you simply pitch to maintain a certain maximum thermal load so you don't burn up. You then, after you've passed through the hypersonic phase, you then pitch to maintain a maximum G load so you don't crush your crew. Finally, you level out, and then you pitch to maintain constant altitude until you've let off your velocity, where you do a lofting maneuver and then touch down. The methods of optimal control allow a trajectory to be computed precisely and numerically using a boundary value solver on an ordinary computer in MATLAB. It does not require an enormous computational cluster. It does not require something which you can't put in a spacecraft. One other example by my college is, if you want to hear more details about this, is getting a Dragon spacecraft down not from low Earth orbit, but from interplanetary space. This turned out to be a critical contributor in our architecture for the Inspiration Mars project, which we'll be presenting on this Saturday. If you want to hear more about the details of what was involved in solving this problem, we'll be presenting at 5:30 on Saturday, second to last group. We're the last group. But it was a critical enabler in taking a vehicle which was only designed to land from LEO on Earth and allowing it to land from interplanetary space on Earth with minor modifications. So where does this leave us? So there's 2 groups of conclusions I want you to take out of this. The first one is just about EDL in general, and it's we do not yet know how to land payloads more massive than 1 ton. We've been working on it for a long time, but we haven't had the breakthrough that we really need. And this is a problem, a very big problem, because every crewed architecture that's been proposed requires considerably more than 1 ton, and not just a little bit more than 1 ton, a lot. The lowest proposed landing mass, that I've seen, is Mars 1's plane, which is planning to use the Dragon and land the base incrementally in pieces and assemble once it's on the ground, is 6 tons. So a factor of 6 improvement is required to make this work. And if you want to do something like Mars Direct, that's a factor of 28. This is not a problem we can just brush aside and say we'll solve it when we get there. This is a defining problem. This is the bottleneck, you might even say, in getting human beings to Mars, at least in my mind. And incremental improvements to existing RDL methods are not going to solve the problem. It is going to require a completely new development, and optimal control theory is a way to enable that. Now, in tagging along with that, we have not seen the necessary improvements to this problem in order to solve it. When MSL touched down on Mars, the code that was running inside of it is the same. It has the same structure as the code that was running inside the command module when it landed on Earth. And again, the reason for that is because Iterating EDL design is an expensive and dangerous process because it can mean the loss of the entire vehicle. But if we could provide a way to test and validate a vehicle and prove that we are working in a robust environment and an optimal trajectory, like optimal control theory provides, that might provide a better way to design these EDL systems. So optimal controls offers several advantages in this field, including the ability to rapidly recompute your trajectory in the event of a deviation and set your spacecraft down without forcing it to follow the pre-computed trajectory, which may no longer be the right answer. It also allows for further precision in landing site selection, since that is, of course, a basic control problem where perturbations are one of the principal sources of error. So the conclusion is basically to stay tuned. We're working on this. There are many master's and PhD theses riding on the idea of it, and we hope that this will be a critical part, providing at least some of the solution to getting our EDL limits up by the factor of 20 or so that they need to be before we can really start landing humans on Mars. So thank you very much.
I've included a major section on EDL starting back in 2010 with my Access to Mars project. So the question I have is, currently there are no GPS type of satellites in orbit around Mars, but they can sort of locate where they are by radio signals and other means. But if you're going to land repeatedly in the same very close area, say within a kilometer or two of a Mars base, you don't want to land any closer than a kilometer to the base. But I assume you're going to have GPS satellites in orbit around Mars and a beacon at the landing site so you can home in on it. So how much of an advantage does that give to the electronics on the descending spacecraft than just landing like your current landing with Curiosity with no absolute way of knowing where you are?
It would be hugely advantageous. The problem is not so much that we don't have the satellites around Mars. The problem is you're inside this plasma sheath, which is shielding the GPS signal from getting to you. So it is. That would be nice if we could use and if we could get absolute true positioning.
What about a laser beam signal?
Well, I wouldn't want to try to design that system.
They're starting to use laser beams for communications already.
Well, communications, yes,
Yeah.
but you're trying to hit a target which is moving at Mach 5 inside a plasma sheath. That's a fantastically difficult problem. At the moment, EDL, your position during EDL is interpolated via accelerometer data. That's currently how it's been done.
It's more of a comment, but using I'm trying to answer his question. Tried to, anyways. GPS satellites would help because say you use the lifting body concept, which has the aspects of an airplane, or it has the characteristics of one, and that you can follow an instrument approach plate like any other airplane does here on Earth. You could do the same thing. The shuttle did it. The shuttle did it the same way. Came through, communications and trajectory data was kind of preloaded onto the shuttle, and then by the time it got through the atmosphere, it followed a flight path all the way back to the landing facility. And I'm pretty confident that out of all of them, I would say that a lifting body would have a good chance at executing heavy payload, deliveries to approximate landing, because you'd be replicating that process.
Sure. Well, that's what DRA-5 assumed. But the problem with a lifting body is its dead weight.
Yeah.
It's a heat. It is more than just a heat shield that you can jettison when you're done. It designs, it informs and controls the structure of the entire spacecraft. So we're looking at a lifting body. It's one of the many solutions, but we don't know what the right solution is yet. We just don't know. And the point of this method is to provide a rapid way to test your solutions to see if they're the right answers.
I'm pretty sure the ESA is trying, with the IXV, the ESA is going to find some answers.
That's for Earth. That's for Earth EDL, I believe.
Oh, okay. But do you think it could apply to Mars?
Can be used as what? I haven't heard about that, but as to your first point, yes. In fact, that is what that is where the smallest one of these numbers comes from. Mars 1's plan is to land the entire base with Dragons, and each of those has between 5 or 6 tons of dry mass. There is a lower limit to that. You can't land a base in 1 kilogram increments and then reassemble it. So there is a lower limit to that, and in practice at the moment that lower limit is around 5 to 6 tons, which is still 5 to 6 times bigger than anything we've landed on Mars. So it's not 26 times bigger, but it does make the problem a little more manageable.
Yes. Have you looked at the hypersonic or supersonic Skylab, the Phobos supersonic Skylab?
No, we haven't.
It'll drop payloads at about 1,200 miles an hour.
What's that in real units?
Huh?
1,200 miles an hour. What's that in real units?
In real?
He means
metric. Come on, man, metric.
Scientific.
About, I think that's about 2 kilometers. And the cable to payload ratio for stuff we could go and buy at 100 tons quickly. Available now is about half. So the cable weighs about half the payload.
Well, it sounds really cool. I won't deny that. I mean, the space elevator sounds really, really cool. I'm not sure about its practicality. It would seem to only limit you to equatorial landing sites, which is kind of limiting.
You actually can swing it sides and stuff, so you can go
Well,
ways off, but yeah.
Well, I'm a huge space tether fan. I would not say no to seeing something like that. But in terms of practicality, I don't know. I couldn't evaluate it.
If you just one payload, it doesn't make sense, but if you're breaking it in many, it does.
Yeah, I know you're in sort of a work in progress as you ended your speech. Given that we have the advances with computers, we can simulate a hypernova, evaluate combustion instability in a rocket engine. Are you looking toward producing a program to where you can simulate this, to where you can, in a way, validate it without having to go out and try it?
So,
I mean, is that your end? What's the end game here? Because is what I'm asking.
So
I see
we
it.
try as much as possible to keep our models as close to analytical physics as accuracy will permit us. One of the things which is kind of a real problem, at least as we see it and as our advisor sees it, is that it is all too common to throw everything into a really fine mesh and just say, there, that's the answer to the problem.
I wasn't saying that.
So we try to steer away from CFD and really complicated meshing and modeling in that field, just because it deprives you of the necessary intuition and realistic connection to seeing what the optimal solution is. So there are people who are doing that, but it's not us.
But you do or do not then see some sort of modeling program.
Sure.
If doing it in computer.
Sure. I mean,
you
I
approve of it.
I'm sure it will be developed eventually, but
Okay.
it's I don't think it's going to be a silver bullet any more than CFD has been a silver bullet for aircraft design in general. It helps, it definitely helps, but it doesn't tell you the right answer to how to design an aircraft.
Wow. Okay, thank you.
Yeah. Musk has already demonstrated a limited form of supersonic retropropulsion with his Falcon 9. Of course, we don't know exactly how high and how much thermal stress was put on it, but the rocket engines relit and worked twice, so we know that much. So we know that we can test with a suborbital sounding rocket with a scale model payload supersonic retropropulsion using the correct speed, which of course is less than 3,000 meters per second at the right height in the Earth's atmosphere. So you can test sections of the flight regime very easily on Earth.
You can test very small sections, but even on Earth, the situation is still completely different. One of the biggest challenges of supersonic retropropulsion is getting the chemistry right. the interaction between the shock and the plume is governed not just by the density of the air, but by the composition of the air. And there's
Right.
nowhere on Earth where you can go to mimic the composition of Mars's atmosphere. So SRP is a very complicated field. It's one of the ones that has benefited a great deal from CFD, but there is nowhere in Earth's atmosphere that you can do a proper test of an SRP system that is designed for Mars. You have to either go to Mars or just brute force it with a raw CFD program.
Well, of course,
Because like you pointed out, Falcon 9's lower stage is purely suborbital, and that's a huge difference to Mars. If you're going, let's say, 5 times faster on Mars, that's a factor of 25 difference in terms of
right, but
dynamic
if you
load.
do a suborbital, you can exactly duplicate the reentry velocity at the right altitude.
Well, it's not just about entry velocity, though. There's more that you need to simulate than just the dynamic pressure and
Yeah.
re-entry velocity. Okay, thank you very much.